Okay, so important theorems. I think last week I handed you guys the summary sheet that has spring, fall, and major theorems. So let me just bring that up just as a visual for these theorems that I want to review with you. Okay, so extreme value theorem says that if a function is continuous on a closed interval, then there must be an absolute max and absolute min somewhere on that interval. Okay, here's a visual example. Let's say I had a function that's continuous. It does not have to be differentiable. Okay, it just has to be continuous. There can be sharp turns, but as long as it's continuous, we're guaranteed that we're going to be able to find a point that is high, that's the highest point, and a point that's the lowest point. There may be shared highest points. That's okay, but at least we can pinpoint that there is a physical location. And to find the highest and lowest points, all we need to do is identify the candidates and test them. Okay, this is assuming that we don't have the graph in front of us. If the graph was in front of us, then there will be no need for extreme value theorem. We can just pinpoint what the highest and lowest points are. But without the use of a graph, we can just identify the most important candidates and then test them. So the candidates that we're testing will be the endpoints, because the endpoints is possible for any endpoint to end up being the highest or lowest point on the graph. And then the critical points. So critical points is where we want to look for locations where the slope is 0, and also locations where the slope is undefined. Because you can tell by looking at this instance, it's possible for a slope undefined location to end up being the lowest or highest point on the graph. So to find critical points, we set the derivative equal to 0. If we set the numerator of the derivative equal to 0, we're able to locate places where slope is 0. If we set the denominator of the derivative equal to 0, then we are locating where the slope is undefined. Okay, so here are the steps. Oops. First, confirm that the function is continuous on the closed interval. Make sure that if there's a vertical asymptote, make sure that it doesn't interfere with the interval. If an asymptote interferes with the interval, then we have to stop the problem and say that extreme value theorem does not apply. Okay, so once our continuity statement is set, we are going to find the endpoints. So we'll identify the endpoints. The endpoints will be provided for you in the problem. Then identify critical points. So to find critical points, we set the derivative equal to 0. If there's a numerator, numerator with a variable, we set that equal to 0. If there's a variable in the denominator, we set that equal to 0 separately. And we want to make sure that all critical points are inside the interval. If a critical point is outside the interval, then we remove it. It's not part of our candidate list anymore. Last, we test the endpoints and the valid critical points into our original function to determine the max and min value on that closed interval. So number 1, let's practice an extreme value theorem problem. Okay, so let's find the value of the absolute extrema on the interval from -2 to 3, state the theorem and conditions. So if I want to find absolute max on the closed interval, that's automatically extreme value theorem. So we know we're using EVT. The only condition that is we need to worry about is continuity. This is a polynomial. Polynomial has no issues with continuity or differentiability, but we really only care about continuity. So we just have to say our function is continuous on the closed interval from -2 to 3, brackets. Okay, we already know that we're going to be testing endpoints, but we also want to test critical points. But we need to first find critical points. So to find critical points, we're going to find f prime. This is a polynomial. There's not going to be any variable in the denominator, so it's just going to be the numerator that we have to worry about. So we find f prime. Easy power rule here. And since we only have the numerator, we're going to set that numerator of f prime equal to 0. We're looking for slope zeros. For this problem, there's no chance that we're ever going to have a slope undefined, so just have to focus on the numerator. I can factor a 6 out. Continue factoring. Solve for x. All right, we have to make a decision here. Do we keep all the critical points? Are all the critical points safe inside the interval? Yes. Okay, so we're gonna test both critical points. If a critical point was outside the interval, we would remove it. What if both critical points are outside the interval? What if all critical points are outside the interval? Does that mean that EVT fails? Okay, so all that means is if your critical points don't fall inside the interval, if none of them do, EVT still applies. It just means that you only have to worry about testing 2 critical points or 2 endpoints. Okay, so you may or may not have critical points to test depending on if they land inside the interval or if you find any. But in this case, we have 4 to test, and they all go back into the original function. Make sure that you don't insert them into the derivative. If you do that, it'll tell you the slope, but it's not going to tell you the max and min. The derivative is only good for finding critical points. After that, we're going to ignore the derivative. It's not going to help us anymore. So we're going to test our candidates. So test the endpoints, test the critical points, and test the other endpoint. They all get inserted into the original function. I'm just going to speed up this process. So -2 in for all the x's of the original function will get me -3. -1 for all the x's will give me 8. 2 in for all the x's will give me -19. And then 3 for all the x's will give me -8. Okay. Now, absolute max and absolute min, we only care about the y value. Okay. So what's the absolute min value? It's -19. Okay. Don't even worry about the x. Okay. Absolute max value is what? 8. Okay. Now you may be tempted to do order pair, but on the AP exam, if it's EVT, they're asking for the y value. So imagine this is a multiple choice question, and the answer choices for absolute max included 8 and -1 separately. If you choose -1, it would be incorrect. Okay, it's the x value of the max value, but it's not the max value. So 8 will be the correct answer. -1 would be incorrect. So it's a little cryptic, I know, but the word value is representing y value, not x. Okay, mean value theorem. Mean value theorem says if a function is continuous on the closed interval and differentiable on the open interval, so now we do need the graph to be smooth curve. Okay, so differentiable means smooth curve. Then there exists a number c on the open interval such that the slope between the endpoints is going to be guaranteed and going to be found somewhere along that curve. Let me show you a visual example of that. So let's say we have a smooth curve, no sharp turns, no asymptotes, no holes. We can guarantee, this is what mean value theorem guarantees. It says, first find the slope between the endpoints. That just means So there's no calculus here, there, right? We're just finding slope between the endpoints. That slope could be 2, it could be 1/2, it could be 3. But whatever slope we find between the endpoints, we know that that slope must exist somewhere along that curve. And what mean value theorem does is it finds that location where that specific steepness that we're looking for can exist on the curve. So here are the steps. We're going to first identify the slope between the endpoints. So you're always given the endpoints, plug into the original function, and just focus on finding that slope. No calculus in the beginning. After you get to that number, then you can set that number aside, and we'll come back to it. We're going to next find the derivative of that function, f prime, and then we set the derivative equal to the number that we found at the very beginning. When we do that, we're able to ask the derivative function to give us the location on the curve where that specific slope value, that steepness, is going to exist. And then finally, we need to make sure that when you find those critical points, that those C values, that the location you're looking for sits between the endpoints. Okay? So we always have to, whenever we find our answer, we also have to go back and double check. Okay, does it live inside the interval? If it doesn't, we have to remove it. Okay. Okay, let's look at number 2. Let the function defined by f of x equals x plus natural log of x. There's our curve. What's the value of c for which the instantaneous rate of change is the same as the average rate of change? Okay, so here's our formula for mean value theorem. Now, there's something about number 2 I want to point out, is that it doesn't explicitly state mean value theorem, but it does describe mean value theorem very clearly. And here is how they are. Sometimes you may be able to see mean value theorem being asked of you without stating it explicitly by these words. Instantaneous rate of change is the same as the average rate of change. So whenever you see instantaneous rate of change equaling the average rate of change, that's describing this right here. Okay, instantaneous rate of change is the derivative at a point. Average rate of change is the slope between endpoints. So that's how they're able to describe mean value theorem without explicitly stating it. Okay, so first things first, let's find the average rate of change. Let's find the slope between the endpoints. But before we can find the slope between the endpoints, we have to first find order pairs so that we can find some y values. So insert 1 and 4 into the original function so that we can find those endpoints. So f of 1 and f of 4. F of 1 is 1 plus natural log of 1. Natural log of 1 is 0, so 0 plus 1 is 1. F of 4, insert 4 into the original function. Insert into the calculator, you'll get 5.386. And now we're going to find that slope that we want to target. So change in y over change in x. So all this time, no calculus yet. We're just gathering information from the order pairs. Oops. That's my bad. I subtracted the x's. 5.386 minus 1. All right. Y2 minus y1 divided by x2 minus x1. Okay, we get 1.462. So that is my average rate of change. Next up, we need to find f prime. So find the derivative. All right, x becomes what? 1. Natural log of x becomes 1 over x. So that's our instantaneous rate of change. So I'm color coding it. Anything that is instantaneous rate of change, that's derivative related. Average rate of change is slope related, or average slope. So we're simply just going to set these equal to each other and solve for x. All right, so we're setting the slope, this 1.462, equal to the derivative, and in return, we're going to be able to find the location where that specific steepness is going to live on that curve. Now, this is easy enough to solve, so we can just solve for x, but if it's a more complex derivative, then what you would do is you would do 1 plus 1 over x minus 1.462. You would set equal to 0, and you would actually graph this. You would graph it, and you would see where that graph is going to intersect the x axis. Find the x-intercept. But being this this problem being relatively easy to solve, we can solve it by hand. But if it's more complicated, then make the calculator graph it and find that x-intercept for you. Okay, but I'm just going to solve it from this perspective. Cross multiply. So somewhere between 1 and 4 at 2.164, the curve of the graph is going to be exactly a steepness of 1.462. Yes.
Did we have to state that f of x is differentiable?
Yeah, that's a good question. This is a multiple choice question, so it didn't really matter. But yes, if it was free response, then that's a good point. We do need to state that our function is continuous on the closed, so bracket 1 to 4, and then differentiable parentheses 1 to 4. Yeah, for response, we do need to make sure that we are we're stating our conditions to fully indicate we're using mean value theorem. So now Rolle's theorem, let's talk about Rolle's theorem for a moment. Rolle's theorem is virtually the same thing as mean value theorem. The only difference is that it's asking for a more specific slope. Here, the slope between the endpoints can be anything. It could be 1, it could be -5, it could be some decimal. But with the Rolle's theorem, we're looking for a slope 0. And because we're looking for a slope 0, these endpoints have to be more restricted in the sense that these endpoints have to produce the same value. If the same values occur, then we know the slope, that means the two graphs, the 2 points are directly across from each other. And if the graphs are directly across from each other, then we can guarantee that there must be a slope 0 somewhere along that curve. Okay, so that's the only difference with Rolle's theorem. Rolle's theorem is we're still plugging endpoints, we're still using the same formula, but these endpoints have to be the same y value. Okay, that's the only way we can guarantee slope 0. Mean value theorem, it can be anything, because we can just turn around and find any slope that we're trying to look for. So just think of Rolle's theorem as a more restrictive version of mean value theorem. The endpoints have to be the same y value. Okay, so let's look at number 3. Let f be the function given by x cubed minus 9x plus 1. You got a polynomial. Find all the numbers that satisfy the conclusion for Rolle's theorem such that f prime c is equal to 0. Okay, so we have 3 conditions now with Rolle's theorem. We need a statement about continuity. We need a statement about differentiability. And then we also need to confirm that the endpoints are actually giving us the same y value. Okay. Polynomial, so you know that your first 2 conditions are good to go. I'll go ahead and write those to the side here. Our function is continuous on the closed bracket, differentiable on the open. Next up, let's find the endpoints, just like how we did with mean value theorem. Remember, as you do this, no calculus, no derivative, okay? Make sure that you are inserting into the original function because we're trying to find the slope between the endpoints. I see a lot of students do this where they do f prime of 1 and f prime of 4. Okay, we don't want to do anything with calculus. Okay, the only thing you're doing with calculus is you're going to find f prime and setting it equal to the slope, but you first have to gather information from the function side. Okay, so let's plug in f of 0. 0 minus 0 plus 1 is 1. Plug in 3, I get 3 cubed is 27. 27 minus 27 is 0. 0 plus 1 is 1. Okay, these numbers match, so that's good. That means Rolle's theorem is gonna apply. Right? We have 2 points that are directly across from each other, which means that we can draw a horizontal line between them, which means that there must be a point on the curve where the slope is 0. Okay. So we have this side figured out. We know this side is always going to be 0 because if my endpoints are the same, then the 2 y values subtracted will just give me 0. Okay. Find f prime. Derivative. Oh, make sure that you're not setting f prime equal to these numbers. Right? You're setting f prime equal to 0 because 0 is the slope that lives between these 2 endpoints. Right? We're always setting f prime equal to 0. So make sure that you're not setting it equal to these numbers here. Okay, divide both sides by 3. Take the square root. Now, what happens, though, if I take the square root? What's going to show up? Plus or minus. So there's actually 2 potential locations here that have slope 0. But do we keep both of these locations? Negative is not, right? So we only care about, even though this is a place that has a slope 0, we only are concerned about the interval. This goes for mean value theorem, for Rolle's theorem, for extreme value theorem. We only care about what's inside the interval. Anything outside is not part of the problem. Okay, so this one is out, just positive root 3. Okay, let's go to some of the homework. This is on page 11. Sorry, page 11, number 3. Okay, number 3 says let f be differentiable functions. So if you see the word differentiable, then it also assumes continuity. Okay, so they don't have to say continuous and differentiable. They can just say differentiable, and then you know that it must also be continuous. So we know it's a smooth curve. So basically continuous and differentiable. And endpoints are provided, 0, -4, and 10, 11. Which of the following must be true for the same C in the value from interval from 0 to 10? It says f prime of C is equal to 0 since extreme value theorem applies. So extreme value theorem tells us, I mean, we do set f prime equal to 0, but the purpose of it is to find absolute max, absolute min. There's no indication of that. Okay. Now f prime of C equal to 0, this is more of Rolle's theorem, right? But why does Rolle's theorem not apply for this problem? Yeah.
Because y's don't equal.
Yeah, y's don't equal, right? So we know this is not a good setup for Rolle's theorem, but it is good enough for mean value theorem. Okay. So I know A doesn't say anything about Rolle's theorem, but I just wanted to make a point that we can't guarantee slope 0 because the endpoints are not matching. Okay, mean value theorem though can apply because all it requires is endpoints figured out, smooth curve, continuous. So again, here's the formula for mean value theorem. Does this match mean value theorem? 11 minus the -4 over 10 minus 0. That's what's required, but here there's a plus sign in between. That plus sign is fixed for C, so that slight difference makes B incorrect. So it has the right idea, it just doesn't quite apply the slope formula correctly. So this one is correct. Okay, let me talk about why D is incorrect. It says IVT applies. Now, IVT doesn't give us anything about the derivative. Okay, what it does is that it tells us between 0 and 11, you see the endpoints as order pair 0, -4, and 10, 11. The mean value theorem says every y value between 0, well, between -4 and 11 is going to be touched at least once. But here, that's not anything with IVT. So answer is D. Sorry, answer is C. Okay, number 4. Let the function be given by f of x on the following interval, which can mean value theorem be applied? So mean value theorem requires continuity and differentiability. Do you see any potential issues with the setup that this function is giving us? Yeah, there's vertical asymptotes. Now, vertical asymptote doesn't mean that mean value theorem can't apply for the entire function. It just means that it can't apply if the mean value theorem is, if the asymptote is somewhere inside the interval. So we know there's a vertical asymptote, 2 of them. So 4 and -2. So let me kind of show you where that could live here. So if I want to do mean value theorem, it's got to be either in this middle region, this region to the left, or region to the right. I can't have mean value theorem that is cutting across the asymptote. So let's see which can be applied here. Oh, and also, by the way, this is a rational function. So rational function, there are asymptotes, but we don't have to worry about any sharp turns. Okay, the only time you got to worry about sharp turns where the function is not differentiable is if there's a radical in the denominator or if you're dealing with an absolute value function. That's the only time. If it's a rational function, you're safe. The only thing you have to worry about are the asymptotes. Hey guys, we're going a little bit longer today. Because of the secure test schedule, we're going to 1028. Okay, so our we have a little bit more time. Okay, trying to make sure you guys know. So mean value theorem is good for any region to the left of the of the vertical asymptote. In between is okay, and to the right is okay. Okay. So between -1 and 3, are we safe? All right. It doesn't cut across any asymptote, right? So we can check that off. That one's good. How about between 5 and 7? Yeah, 5 and 7 were okay because it doesn't include the asymptote. How about 1 to 5? Yeah, 1 to 5 is an issue, right? If I want to go from 1 to 5, I'm going to have to cross over that asymptote. If I cross over an asymptote, then I can't guarantee continuity in that interval. Okay, next page, page 12. Okay, select values of a continuous function. So we know that it's continuous, no breaks in the graph, no asymptotes, no holes. Which of the following could be false? By intermediate value theorem, there's a value such that f of c equals 10. So if you think about this graph here, we're going from y value of 1, and we're ending at y value of 31, and the graph is continuous. Can we guarantee that there is a point where there's a y value of 10? What do you guys think? So 2, 1. So if we're going from 1 to 31, are we going to hit a y value of 10 somewhere between? Yes, right. Because they tell us it's continuous. So IVT is good, but we're looking for what could be false. So even though that's correct, that's not a false statement. So we'll move on. But mean value theorem, there's a value such that f prime of c is equal to 10. Can we guarantee a slope of 10 between the endpoints? Well, let's test the slope here. Change in y over the change in x, right? We're just looking at the slope between the endpoints. So y2 minus y1 divided by x2 minus x1. Okay, so I do see a slope of 10. So does mean value theorem apply? I'm able to find that slope of 10 here. But it's a little bit tricky here. What are the conditions for mean value theorem? And differentiable. So the tricky thing is they say continuous, but they don't say differentiable. So there could be a sharp turn somewhere along this region. Even though the slope ends up being 10 between the endpoints, there may be a sharp turn that could derail that. So there's no mention of differentiable or differentiability. So there has that possibility of could be false. So this is actually the answer there. Okay, part C and D are true because EVT says that we're guaranteed to get an absolute max. So f of c is less than or equal to f of x, just indicates that there's going to be a physical maximum point. And then f of c is greater than or equal to f of x, just indicates there's going to be a guaranteed absolute minimum It's just a kind of a strange way of saying it, but EVT, all EVT requires is it requires continuity. It doesn't require differentiability. So IVT only requires continuity. EVT only requires continuity. It's only mean value theorem and rolls that requires differentiability because it's slope related. So to guarantee a slope, we got to ensure that every point has a slope that exists. Okay, last one here, number 6. Okay, let the function be given by f of x on the closed interval. How many values of c satisfies the conclusion from mean value theorem? Well, mean value theorem requires continuity and differentiability. Natural log is safe as long as we're in the positive region. There's no sharp turns here. Remember, sharp turns is only if you're dealing with radicals in the denominator. So we're safe, but we do need to, let's just go ahead and state our conditions here. We know our function is continuous. We know our function is differentiable. And the first thing we need to do is look for endpoints, right? So no calculus yet. We're just inserting our endpoints into the original function. So we'll find f of 0, and we'll find f of 8.
That's fine. You can come in. Everything is kind of pushed out today's schedule. Okay, you'll do it now.
Yeah.
The makeup for which the chapter 5 or for
Yeah.
Okay.
Okay, so f of 0, insert into the original function. I get 1. Plug 8 into the function. Natural log of 8 squared plus 1 with cosine in front. That'll just give us a decimal value, so negative 0.512. Okay, we're going to take the time to find the slope. So change in y over change in x. And that slope ends up being negative 0.189. Okay, so this is what we have. We have the slope. We're going to set that number aside. And now we're going to turn to the derivative. So to get to the derivative, we have to go through chain rule. Cosine of u becomes negative sine of u times u prime. So u prime is 2x over x squared plus 1. That's natural log of u is u prime over u. So what we have is we have the derivative, and now we're just going to set the derivative equal to the slope. And we're going to ask the function to tell us, ask the derivative to tell us where does the slope live. Now this one is difficult to solve by hand, so we're going to make the best use of the calculator. We're going to graph this. So the way you want to graph it is you want to bring everything over to one side and set equal to 0. And you're going to be graphing this. And as you graph this, you're simply looking to see where is this graph going to hit an intercept or hit the x-axis between 0 and 8. So the graph may look something like this. Between 0 and 8, it's going to hit 2 locations. And when it hits those 2 locations, you know it's safely between 0 and 8. We don't really care about the solutions. We just want to know how many times it actually hits the x-axis, and it's twice. Okay, so for homework, I'm just gonna be checking pages 10, 11, and 12. So you just have to finish up number 8. We've done most of the homework, and I'll check that tomorrow. I'll send out a reminder this afternoon. So again, pages 10, 11, and 12.
During this coming
Yeah,
period?
sure. Are you taking you're taking the recovery, right?
Yeah.
All right.
Should I go to the boss?
Yeah, you can sit from the-